Il fait froid ici. Bon.
Maintenant, oui, quand j'ai ouvert, c'était super chaud et dégueulasse.
Ouais, je crois qu'on peut. Oui, on peut mettre le chauffage.
Non, non, il manquait l'air.
Il n'y a pas de la clim aussi dans cette pièce.
Ouais, mais c'est pas
Le jour aussi, j'avais froid, mais je crois que c'était fermé. C'est la clim ici.
Oui, oui. Cosmological Correlators, theory and phenomenology.
Ah non.
Hello. Good morning. So please, so I remind you that the next lecture will be on Friday at 10 o'clock. And so if you need to lunch and you don't have a restaurant card, the lab will pay for you. Well, I'll see what the story. I said if you don't have a So I'm not totally out of the woods with my 4 hours of lecture was not very good for my throat. In hindsight, it's probably I didn't know I was going to be sick, but I'm much better. But bear with me. So. Okay. Can I or please? Good morning, everyone. So just to recap, our interest is to, at the end of inflation, compute correlation functions of density perturbations, which is ultimately a problem of quantum field theory in a curved spacetime, which at least today will take to be either de Sitter space, an approximation to inflation, or actually we're going to take a step back and to warm ourselves up and do these computations in flat space. And if that raises a red flag, oh, isn't it a scattering amplitude? The type of objects that we compute are either expectation values of operators at equal time, because that mimics the imprint of quantum correlations at the hot Big Bang, or the wave function of the universe at some fixed time. So it's not a scattering amplitude, it's a different type of object. So what we need to explain the data from phenomenology, as I explained to you last week, is just the 2-point function, which is consistent with free field theory of a very light scalar. Okay, so all we really need is this 2-point function, and the kinematics of the Sitter spaces I'll show you later today. It's a time translation symmetry is enough to explain the almost scaling variance that we need. We need the mass in Hubble units of this scalar to be much smaller than 1. Now we spent quite a bit of time. So this is what we need to explain our universe. But we would like to understand what this field is made of, where it comes from, and probably the only tool. If you read the abstract of the course, it's rather dramatic first statement that all information we'll ever learn from the early universe comes from cosmological correlators. And that's probably true. And if you really want to understand where this scalar field comes from, you need to study higher point correlation functions. So I focused on the 3-point function. And try to unpack the different types of scenarios. And one possibility.
No, it wasn't a question.
Okay. One possibility is just self-interactions. what we call equilateral non-Gaussianity. So this is, of course, Gaussian. This is going to be non-Gaussian. That's one possibility. And the other possibility, well, there's a whole umbrella that I was trying to sell to you. One is that there's some weakly coupled physics that talks to the scalar fields. For example, induce linear mixing, and then decay. So you'd have this type of correlation function, or a bit of a road that less explored is to consider more general two-point function that comes from some strongly coupled sector. Of course, this includes loops, etc. But I would put that into the weak coupling umbrella. But you could imagine that there's some strongly coupled sector, and you exchange some sort of two-point function. It is a strongly coupled sector. Okay. So this is the most explored thing. But I think they're both equally interesting. Okay. Very good. So that's where we stopped. And I started describing the formalism to compute these things. One is if you really want to find this observable, then you want in the interacting vacuum state to compute expectation values of the density perturbations. For example, here it's something like this. This all evaluated at some late time, eta star. The only important thing is that in order for this to be efficiently produced by the expansion of the universe, you want their physical wavelength to be much bigger than the intrinsic scale of the sitter, which is the Hubble radius. So you always choose eta star such that all the k eta stars are all much smaller than 1. Okay? And so this is we call this super horizon. I think I briefly introduced it's just saying that you underwent so much redshift that you already had a burst of particle production, and these correlations are imprinted at very large distance scales. So this is one possibility. If you want to directly compute this, then you should use the Keynesian Schwinger-Keldysh formalism. But then there is another object which is interesting and useful, which is the Hartle-Hawking. So this is Schwinger-Keldysh. Then there's the Hartle-Hawking wave function of the universe, which I guess I was calling it psi, like this, psi with like 2 wings. This is the wave function of this state, where now you ask different type of question. You ask what's the probability, what's the amplitude of probability of the universe to have a given shape at time eta star. And then you can use the Born rule. So you use the Born rule to connect to this type of expectation. So that's to say that the wave function packages more information than the expectation value. But it's a convenient object to study also because it has nice kinematic properties. The wave function coefficients, they satisfy the same kinematics in the sitter, for example, the same kinematics as correlation functions in a conformal field theory. Yes.
Is it a vacuum state well defined, the Sitter space?
You weren't here, no, when I discussed this. How do I say this? There's one state in which the computations make sense. I wouldn't call it vacuum. That's the short answer. I mean, there's no vacuum in the sense of a Hamiltonian that's positive, bounded from below, that you minimize. There's one state that at short distances has similar correlation functions as those in flat space and respects all the Sitter isometries. So that's the state that we use. But it's not a vacuum in the sense of minimizing the Hamiltonian. And if you do interaction field theory, and you have some prescription, etc., it seems that everything is fine. Now, there's the famous objection of this due to Polyakov, which I think is not fully settled. Let me explain. And I have nothing to say about this, even though it every day when I wake up, it's still like scratching the back of my head, which is the following. So when we do perturbation theory, we use the I-epsilon prescription, and eventually we see this as an accounting trick to do the compute correlation function in the interaction theory. However, if you see the I-epsilon as some physical process where you adiabatically switch on and off interaction, then of course you break the isometries of the space-time. As you start to do some theory. So I guess everyone is happy to, even here, if there's no way to minimize the Hamiltonian, you can find this Bunch-Davies state, the state that preserves the Sitter isometries. And then you can imagine switching on interaction. And then you would like to make sense of expectation values in perturbation theory in lambda. But then one thing you could do is to make this coupling constant switch on and off, right? So you make it in the past, so you give it some time dependence. So that if you plot here time, lambda of t, something like this, right? You would think that for all wavelengths that you're trying to correlate, then maybe this thing is active as they cross the horizon. Then when they cross the horizon already for many e-folds, you switch it off again. Of course, so Polyakov's claim is essentially the following: if you do that, you explicitly break the Sitter isometry, right, because there's some time dependence. So you introduce some scale that controls the breaking of the Sitter isometry. And his claim is that if you try to send this scale to 0 or infinity in such a way that you try to, for example, send this IR cutoff to infinity, try to make this become more and more time independent, this IR sort of elephant thing does not disappear. That's his claim. So he sees this as a signature of some instability, or at least some big infrared effects. This example maybe is a bad example. Well, okay, if the mass is big enough, then there's no problem. There should be a perturbatively reasonable state at finite lambda. Anyway, so that's the claim, and I have nothing to say about it, because of course, then things will become the Sitter non-invariant, and you need to understand how to keep track of this and really check whether there's this lack of adiabaticity, if you wish. It's clear that he has the QFT in the Sitter has all the ingredients for you to be a bit suspicious about adiabaticity, because even if there's a mass gap, if you study the Hamiltonian, the time-dependent Hamiltonian, you see that when you go close to a horizon, so for example, if you study the Hamiltonian from perspective of these sort of time slices, as you go to the past here, the mass gap is not really helping you, so it is not clear that the adiabatic theorem should work. Same thing if you use the Hamiltonian with respect to static time evolution. But this, I think, is more innocent. It's just telling you that there's particle production as you get close to the horizon. My only point is that the usual adiabaticity type of argument that the mass gap protects you as long as this is low enough, I don't think it immediately applies. Okay.
Did anyone look, sorry to interrupt you. Did anyone look for the stability of this vacuum with respect to quantum situation? Also, you have fields here in the city space. Have this one loop effective action to see whether the vacuum is stable or not? Natural question to ask.
Well, I think the question is whether the one loop effective action is the right object to diagnose this, because even in free field theory, the one loop effective action is a complex value. Right? But it's just the physics of. So what is the one loop effective action telling you? What is the amplitude for you to have no particles here, to end up with a state with no particles here? But we know that there is spontaneous particle production, so this is exponentially suppressed. So there is always going to be an imaginary part. But then the question, I think the big problem is that there is no diagnostics, some object that everyone agrees. If you compute for a black hole, or if you compute for the Schwinger effect, you see a problem. If you compute the same thing for the de Sitter space, no problem. Because the other thing that I find worrisome and tantalizing from Polyakov's papers is that the analogy with the Schwinger effects, because if you take eternal electric field, then so let's say eternally switched on everywhere electric field. So this background, if you do QFT in this curved background, fixed E field, it has time translation symmetry. So if you find a state you can quantize in a way that doesn't break time translation invariance, you never see the E field being destroyed by Schwinger pair production. And that's his essentially the gist of his statements. That maybe you can build states that preserve the Sitter invariance, but they're unphysical. The same way that here you could produce some crazy states. You just keep feeding charges from the boundaries, from the path, from the corners, from x plus or minus infinity to keep the electric field. You keep it soaking so that it never manages to deplete itself. Anyway, yeah, I spent a lot of time thinking about it, but I have nothing useful to say. I think it's an important problem. I don't encourage students to work on it because I think it's a tricky problem. Anyway, we're gonna pretend that everything is fine in the Bunch-Davies state. Okay, going back here. So I will try to. Okay, so what's the problem? The problem is that you run out of steam in this direction relatively fast. So famous benchmark example that now by now is very well understood, but something that motivated going beyond these first two sets of tools is if you study this sort of, or maybe even better. So first of all, this has linear mixing, and linear mixing is forbidden in a maximally symmetric spacetime, but is allowed in slow roll inflation. So there's a nice paper. Well, I think this was always lore in the inflation literature, but it was nicely articulated. I promise no references, right? But in 2014, there's a paper by, let me not, I know a subset of the authors, but there you can ask me. There's a nice paper by people in India where they where they show that the bispectra, the 3-point functions with linear mixing, they are descendants of a more symmetric problem, at least in slow roll inflation. So say you want to study this type of diagram, 3-point function with an exchange, but this is in slow roll inflation. Then one thing you can do is you can go to the Sitter. This is a 4. And study this sort of 2-to-2 type of exchange diagram. Has more symmetry because you have all the isometries of the Sitter space. And then what you do is you take one of the legs and you make it very soft. So let me. By the, so what is the idea? So the limit K4 goes to 0. So there's 1, 2, 3, 4. Of the, for example, the wave function coefficient. In ds, you need to do 2 things. One, you need to send K4 to 0, and you need to make the mass very small, but not 0. Because shift symmetry will kill this, the soft limit. There's a sort of Adler 0. If you take literally K4 to 0, and this is strictly massless, you kill the whole diagram. But if you give it a small mass, m squared much smaller than h squared of this leg, the others you can keep them essentially massless. Then this is essentially giving you the slow roll answer. And the physics is very intuitive. The idea is that this 4th leg is very light, and as you make it very soft, it becomes a background wave for the 3 other hard fluctuations. So it mimics slow roll inflation, which is not exactly the Sitter space. So you should think of this as this creates some background wave. So this creates this background wave. And then it's equivalent to having these 3 perturbations now thinking they are in a slowly rolling background solution instead of the Sitter space. Okay? And so this works beautifully. So actually, very nice example. So as I was praising Filippo here last week, so he did the computation of graviton exchange in inflation. So if you do this exact trick for his computation, you get the only the Newtonian potential exchange here, and you reproduce Maldaceno's result for the 3-point function of slow roll inflation. So you can connect the 4-point function with graviton exchange to the slow roll 3-point function that is minimal, that is always there because of gravity. But this trick always works. So if you take any state, any 2-point function, and you play this sort of game, you get a good proxy for the 3-point function in slow roll inflation. Okay? So it changes this problem to this one in which you have a bigger symmetry handle at your disposal. You have the full kinematics of the de Sitter group at your disposal. Well, here you don't. So that's one thing. So the other thing is that the moment that this particle here is massive generic mass, generic spin, this propagator is complicated. Complicated for the simple reason that the solution of the wave equation in the Sitter space is a Bessel function. So in flat space, when you solve the wave equation, the solution of the wave equation is always e to the I omega t for a given wave number, right? So the only thing that the mass does is it changes the relation between k. So a plane wave flat space is always described by this. However, so this is flat. However, in this ether, that's not true. You take e to the I k dot x, and you get complicated function fk of eta, which is a Hankel function for generic mass and Bessel function. Only for very special values of the mass, if this is massless or conformally coupled, that this object is just the fact that Bessel functions with very particular index simplified. Okay, so generically, for generic, fk is like a Hankel function. I view k eta, where this mu is roughly the mass in Hubble units of the particle. So there are two special cases. They're important, which is m squared equals to 2h squared, which is conformally coupled, in which case you just get a plane wave with some redshift factor, eta e to the ik, and m squared equals 0. I'll lower the board in a second. Fk 1 minus ik eta. Okay. So these are the two cases that we can do the computation explicitly. So if you do gravitons, for example, you can do it in part because of the simplicity of the mode function, but still the vertices are complicated, etc. But for generic mass, if you'd like to do spectroscopy of what was active during inflation, then you run into trouble that even at tree level, you need to do time integrals. You need to integrate over the position of these vertices, and you integrate products of Hankel functions. That you can then go, for example, to, there's this famous book of Watson on everything you wanted to know and more on Bessel functions, and the integrals unfortunately are not there. So you need to develop some machinery. Even numerically integrating this is not so straightforward because they oscillate very fast. Anyway, you can do something numerically, but like to have then you have to generate a plot for every mass, etc. Not very convenient. You'd like to do something a little bit better. And I'll show you that if you understand the kinematic and analytic structure of the answer by looking at simpler examples, you can sort of bootstrap this by finding, instead of doing integrals, you find a differential equation. And this is very much in line with what people in scattering amplitudes do. Often there's like QCD, like loop diagrams, they're complicated. And one very fruitful strategy is to find a set of differential equations that the loop integrals satisfy. Okay. So perhaps not today, but on Friday, I'll show you a toy model in which you can massage at tree level these time integrals in the form that they scream and look like scattering amplitudes at one loop. And then we're going to use QCD machinery to beat them. Yeah.
So these integrals for generic mass, after you do them, do they result in some non-classical, easy classical?
We thought we had invented the functions when we solved for them, but it turns out that they're called Campé de Fourier functions. If that makes you happy, then yes, they're Campé de Fourier functions. If, like me, you have no idea what that means, then no. No, they exist in the sense that if you go to Wolfram, there's something called Campé de Fourier function, and so that's what this will be. Okay.
That means even in the differential equation aspect, like perspective, you would still produce these type.
Yes, that's how we found them. Well, in some sense, Campé de Fourier just means solution of differential equation with some boundary conditions, right? So I'll show you the differential equations and I'll explain the boundary conditions. Now there's something that I'm excited about that I'm writing a paper on right now, which is if you change completely the kinematic space, you move away from momentum space, then you can write this diagram using hypergeometric functions. But that maybe I can tell you offline. I'm not sure I'm able to make it in the lectures. So this, or you go to Rencontre on Thursday. I will talk about this cosmological Grassmannian, which is the right kinematic space to address this question. Okay. So that's the challenge. We would like to just to produce. Well, there's a conceptual thrust, which is like this is a pretty simple diagram, and you'd like to understand better how it looks like, just to understand QFT in the Sitter space better. But there's also phenomenological thrust that you'd like to use this to search for primordial non-Gaussianity that comes from new messenger particles, particles of mass of order Hubble, which could be very high. So we would like to feed to our CMB friends that do this data analysis precise templates. So I'll show you how to do that. I mean, if you just follow the rules of the inino wave function of the universe, then you hit some stumbling block, which is you have to do time integrals of products of Ankiel functions. And we're going to try to get away from this roadblock. Okay, so that's what we're going to do probably for the rest of today. So in order to get there, I need to put some intuition on how these computations work in your head, okay? So there are two parts to the story. One is kinematics and the other is dynamics. So kinematics is boring. So I'll probably just state results for you. But first we discuss dynamics because it's more fun. Okay, let's see. So we're going to start with the flat space wave function. So the model we have in mind, because it's flat space, the mass is not very important. We're just doing this exercise to get a handle on the singularity structure, what the singular points are and what they mean. So I'll make this field be, I'll choose it to be massless, but the mass is not important. You just go to frequency space. And I think that for our purposes, just phi cube is enough. Yeah. So let's start at 2 points. This is the type of diagram you would compute. There's something to start here. So what is the wave function? Psi 2. And because of translation invariance, I'm going to go to momentum space, okay? So even though there's some phi of x, which is the profile of the field at this, so it's the argument of the wave function, I'm going to go to momentum space. I'm going to talk about phi k. There's going to be some psi 2 of k1, k2, phi of k1, k2, okay? At 2 points, I just work with the Gaussian theory, so of course the wave function will be Gaussian, okay? So let's do this computation. This is the most sophisticated way of doing something rather trivial, which is to quantize the harmonic oscillator, but it's useful for the other examples. So what you want is, so what are the solutions of the equation of motion? Remember that the wave function in this semi-classical type of approximation is just the e to the is evaluated on some classical. Yeah, now I was being careful and giving different names to these things. So this is the three. So there's some bulk solution. And the boundary value, I'm giving the name 5K. But this is different things, no, it's apples and oranges, okay? This is the three-dimensional profile. I think I was calling, maybe, let me do it like this. Okay, so there's some four-dimensional field whose boundary value is this var phi. Okay, so I need to compute the action on some classical solution to the equation of motion, and select the vacuum. So what is the most general solution? Phi of the equation of motion. It's for a given momentum. So phi of k eta is just alpha e to the ik eta plus beta. It's the minus ik eta. And you want two boundary conditions. One is that as eta goes to eta star, you want phi k eta star to be equal to phi k, var phi k. And as eta goes to minus infinity in the proper I epsilon, 1 plus I epsilon or whatever, you want phi go to 0. Okay? And therefore, the phi classical, there's only two options, and I always get it wrong, but it's the one that will give you a reasonable answer. Phi classical eta is just going to be into the ik minus eta star. Okay? So you want you don't want a mixture, because otherwise, if you go into the complex time, one grows and the other decays. So you want only one exponential, and you want at eta star this solution to have value phi k. Okay. Now you compute the action. It's a quadratic theory on shell. You integrate by parts, you get the equation of motion. So the only thing that survives is the boundary term. Right? The boundary term determines the wave function. So the action is just going to be integral v3x of phi classical dot integrated from minus infinity to eta star. And very important, which usually for students it causes some confusion, that e to the is looks like a phase, but the saddle point is complex valued, so it's okay. So the wave function is going to be interesting. Going to have a this is not just a pure phase. Otherwise, the expectation values would be trivial. You see from here that you're just taking one oscillatory but complex value solution. So if you do this, then again, if you put I here, then this I will conspire with this I here, and you should get that this is minus you go to momentum space, D3K1. I'm not being careful with the factor of I, but this should be the answer. So this is because of translational symmetry. The modes just talk to each other. They add up to 0, and you get something that goes like K. Okay? So the wave function, so as I said, just the harmonic oscillator ground state. Wave function is the most complicated way of deriving something we've known forever. And okay, this is type 2. Another bit of notation that I think introduced by Maldacena, which is useful. If you put a little prime on an object, you're just stripping the delta function. So that's just to say that the psi2 prime is K1. Okay. So from here, if you use Born's rule, you just get the simplest thing, which is the expectation value of the field at equal times. Notice that it doesn't depend on eta star because of time translation symmetry. So even though this depends on eta star, because the boundary term is evaluated eta star, the eta star drops out. You get this. You should get this with this minus is important so that you get a positive 2-point function. And this is the usual result that you would get from canonical quantization. No? Do canonical quantization, then if you if you take the field phi hat, then it's going to have A, and here you get e to the I k eta plus Hermitian conjugates. But to ensure proper canonical commutation relations, this mode function has a 1 over root of 2k, which is exactly this root 2k that appears here. Okay. All right. So this is pretty trivial. I invite you to do the same exercise for free field in the sitter, which is already a little bit interesting. So free m squared equals 0 field in the sitter 4. Here it's important that you take k eta star much smaller than 1, but not 0. So you need eta star to be small but finite. And if you expand, you get this for psi 2. I'm just stating the result. I mean, I can even write what phi classical is. Phi classical is just 1 minus ik eta e to the I k eta minus phi. So you're evaluating the action on this saddle. Okay, it's just you wanted eta star, the field, to have amplitude phi k, and at the early times you want it to look like a harmonic oscillator, so that when you go into the complex time direction, you get this damping factor. But again, I'm just doing the bunch states related to English's question. Okay. Now, if you compute the wave function coefficient here, it's more interesting. You get, well, let me write the wave function. Okay. That's why you need to keep eta star finite. Let me restore h squared star. H appears because there's h in the action. Minus k cubed over h squared. Okay. I'm stripping out the delta function. Okay. So there's an interesting phase. There's some big oscillatory phase. Some the WKB like a big phase because this is telling that the fluctuations are classicalizing. They got particle produced and they get very squeezed. So this drops out of expectation values, but there's some famous avatar, for example, in ADS. It's related to what's called holographic renormalization. You see that interestingly, even if it's diverging, as you send eta star to 0, it's local in position space. So k squared phi k, just the gradient of phi squared. Gradient in the sense of gradient on this slice. So if you wanted to relate this to some partition function, you can add a local counter term to obtain this naive divergence. Anyway, it drops out of expectation values once you take mod squared. And this k cubed is related to the scaling variance of the two-point function of a massless field in de Sitter space. So here, the two-point function, so inconsistent notation. The two-point function in flat space was just 1 over 2k. The two-point function in de Sitter space is going to be h squared over k cubed, over 2k cubed. That eta star goes to 0, h squared over 2k cubed, which is, as we promised, it's eta star independent, so the modes freeze as they cross the horizon, and redshift doesn't manage to destroy them. So because they are massless, the amplitude survives to arbitrarily late times. If you repeat this exercise for any non-zero mass, you'll find that there is a factor of eta star here. Eta star to a certain power in such a way that the two-point function decays the longer inflation lasts. Okay? Which was if you remember, we solved the Klein-Gordon equation generic times this Bessel function, but if you try to solve it at late times or for eta very small, then you'll find that it goes like eta to the delta with delta minus 3 minus m squared over h squared. So in particular, unless delta equals 0, there's always going to be some late time decay of the mode functions that will be reflected in this expectation value. So far, so good. It's just Gaussian free field theory. Pretty straightforward. Now let's do interacting field theory.
Let's go about boundary conditions. I have questions.
Yeah.
So in the eta goes to minus infinity, you require the field to goes to 0.
That's some regularity when you go into the complex domain.
But usually, like when I think about this one, eta goes to minus infinity. Of course, you're doing it in a flat space, but in the inflationary background, it's going to be a short distance mode function. We expect this to be the mode of a scalar field in the free space. Yes. So I thought naively this has to be like 1 over square root of 2k or something like that.
Yes, but that's true when you do canonical quantization. Here we're just trying to find the saddle point that controls the wave function, and instead what we're imposing is regularity as you go into the complex. I mean, it does resemble the flat space solution, the sense that it's oscillating the same way, but the regularity is more important here. When you do canonical quantization, then what you're saying is exactly right. What multiplies A at early times should look like e to the I k eta divided by root 2k. But we're not doing canonical quantization here.
So you're just asking, this field is a classical field, asking regularity at the
Yes. So you're computing the wave function by saddle point, and then you're finding a classical solution which has these boundary conditions of regularity and the fixed value of the field at late times. So if we continue with an interaction theory, then you'd have to solve the nonlinear equations and plug it back here. And it's a tedious exercise, but thankfully you can read the notes of Bauman and Joyce to see how it's done using Green's functions. But the punchline is pretty intuitive. So I just tell you what the punchline is, and we carry on. If you want to compute, for example, psi 3, what you would do is you introduce what are called bulk to boundary propagators. Before we were imposing that this solution of the equation of motion has amplitude phi k for every Fourier mode. Now we know that we're computing psi 3 for wave numbers k1, k2, k3, so we just normalize, okay? We just put amplitude 1, and we always have in mind that this psi 3 will multiply. So the wave function has its Gaussian part, phi k1, phi k2, and then it has some non-Gaussian part, and so on. Okay, so of course we could introduce the phi's in the propagator, but it's unnecessary. So we just impose that at late times it has a value 1. Okay, so the bulk to boundary propagator in flat space is very simple. Let me call it K. It depends on momentum and some time. There's some eta here. And it's going to be just e to the I k minus eta star. So there's eta star. So it has amplitude. In the past, it behaves like a plane wave, and eta star has amplitude 1. So this is very simple. We would just integrate 3 bulk to boundary propagators over time. There's a single time integral to do, minus infinity to eta star k of k1 Okay, very simple. Now, if we're going to do psi 4, then we need also bulk to bulk propagator. Say we are on the F channel. It's going to be T and U channel, but we also need this is slightly more complicated, but not much more complicated. All you want is that this is a Green's function. You're just solving the equations iteratively using Green's functions. And you already settled the boundary conditions by stitching in this bulk to boundary propagator. So you want this to be a Green's function that when either of these times hits eta star, it vanishes. Okay? So it's not a standard Feynman like Green's function. So it's sensitive to the location of eta star. Now I don't remember the general formula for generic eta star. So let me just work with eta star equals 0 because in flat space, the location of eta star is not important. Okay. Then I can write the bulk to bulk. Let me call it G. So it depends on the momentum being exchanged. So there's K1, K2, K3, K4. Let me call this, I don't know, Y. Eta 1, 2. This is going to have the 1 over 2k that you were just asking me about because it's a Green's function. We usually write this in four momentum notation, but we're going to break time translation symmetry because we need to have some memory of the location of this surface. So then we just write it in standard canonical quantization form. You should take these formulas with lots of grains of salt. I'm not keeping track of minus, etc. Bit winging it. And here you, right, so you need e to the I, y. So this is when eta 1 is bigger than eta 2. You keep this one around, and now you send eta 1 to 0. You have e to the plus iy eta 2, so you want this. So notice how this term here depends on eta 1 plus eta 2. Okay. So it breaks time translation symmetry. But it's clear that, for example, when I send eta 1 to 0, then this term survives. This one is 0. So this goes to e to the plus iy eta 2, which cancels with this. Okay. It's symmetric. So that's what the propagator is. So in this example, so let's go back. So we're going to study this file in a second. So let's go back and do this computation. There's a G here. And if you do this, you will find a very simple formula. This would be identical to energy conserving delta function integral. The only difference is now you integrate up to eta star, which I'm going to set to 0. Okay. So now when eta star is 0, it's just e to the I k eta. And there's an I. Okay, so psi 3 prime is given by this. Now, this is a very simple example, but it already illustrates a point. Psi 3 is has no singularities in the physical region. Okay, so it's completely smooth and in the physical region. However, k is square root of k squared, so you can always change sheet, make this k negative, and outside of the physical region it has a singularity. And when you send k1 plus k2 plus k3 to 0, it blows up. So that's 1 over k. Let me write 1, 2, 3 just to compactify this with this. I'm just calling k1, 2, 3. And let's see, the residue, the leading singularity, is the flat space scattering amplitude, which in this example is pretty trivial. It's IG. Now you can prove that this is a general statement. So any cosmological correlator is a smooth function in the physical region, has no singularities in the physical region. And when you send, yeah, I think we can make general statement, but of course at loop level, one should take them with a grain of salt, because I don't think we crossed all the T's, etc., related to renormalization, etc. So, but for sure at tree level and in examples that have been checked at loop level, in the physical region, the correlator, the wave function, is smooth, has no singularities, and it always has this total energy, the sum of k's. So when you sit on the locus of energy conservation, where you would in flat space get a delta function of energy conservation, you get that the cosmological correlator blows up and it gives you the flat space scattering amplitude of the analogous process. Yes?
Can you recover all of this from double Vic rotations or some analytic continuation of Witten diagrams and these kind of things? Because it seems very like all this computation seems to basically exchange your radial coordinates with time by some nice thing, and
Yes.
everything is kind of similar.
In the Sitter space, yes, you can do that. It's not very straightforward, but it can be done. It was done by various people, but nice papers by Slate and Taron, I think, really settled all of this. It's not clear that it makes the computation simpler, because people say that in ADS these diagrams have been computed. The formulae are not very practical. In particular, they had never been computed in momentum space, so you can't just Fourier transform the answers in position space. Yes. So yes, it's true. Whether it really simplifies the actual computation, I'm not sure. But some people claim yes, but I'm not. I haven't worked on this weak rotation beyond very simple things. But yeah, it can be done. But it's not related to this point, no? This flat space limit, usually in ADS, it's taken a rather different way. You send the ADS radius to infinity. While here, we're trying to send the energy of the process to zero. And when we send the energy of the process to zero, what we're essentially doing is we're making the integral peak at very early times. We're trying to force the integral to peak at minus infinity, in which case you erase the memory of the boundary. So that's why it looks like a flat space amplitude. That's not usually how it's done in ADS. Okay. No, for the flat space wave function, yes. Well, at tree level, now I don't remember if no, it might probably yes, because it's just the delta energy conserving delta function. I don't need to check for at loop level. Yeah, this total energy singularity in the Sitter space, for example, can be either power law or it can be logarithmic. It actually tells you about the UV behavior of the flat space object. So it changes depending on what exactly you have in flat space. But for example, if you studied 4-point self-interactions with more and more irrelevant operators, you would not change anything. The psi 4 would always have a simple pole in K1 plus K2 plus K3 plus K4. That's not true in the Sitter space. If you do irrelevant operators in the Sitter, the more irrelevant an operator is, the bigger the singularity is. Okay, so that's so the Sitter in that sense is very different. But the locus, the place where the correlator singular, is the same in flat or in the Sitter space. Okay. So I will do psi 4 quickly. I'll show you where the singularities are, and then we interpret them, and then we take a little break. Okay. So psi 4, gonna have double integral d1 k of k1 1 k of k2 eta 1 g of y. So you have to do this double integral minus infinity to 0. There are three terms, this, and this, two nested integrals to do. And rather nice, so it has 1 over y singularity, but it cancels against the three terms. So there's already a little miracle that happens here. And the answer, because there's g squared here, the answer is kind of neat. It's this one, g squared divided by so there are three singularities, okay? This one we already found, the total energy one. When you sit on the locus of this singularity, you get g squared divided by minus k1 plus k2 squared plus y squared. And that's just the flat space Mandelstam, right? If you make the fake for momentum, which is k1, k1, null for momentum. This is just b squared over b1 plus b2 squared, which is the flat space amplitude. Okay? So it's just the F channel flat space scattering amplitude. So what's happening is when you do this, you're sending both times to minus infinity. You're forcing the integral to peak when both times go to minus infinity, and then they forget about the boundary, and it looks like a flat space scattering amplitude. Now, when you send, there are these two new singularities, and well, you can guess without even doing the computation. If I send this to 0, what am I doing? So what's entering this vertex? It's k. The energy is k1 plus k2 plus y. So you're forcing this time integral to peak at very early times, but you're not forcing this one. So what you get is a bit of a centaur kind of object. You have something that goes like flat space scattering amplitude on the left, and something that is related to the 3-point wave function coefficient on the right. Okay. What you get in detail is this. You can reconstruct. It's the analog of factorization. So you see the wave function. You cannot sit on some resonance. There's no like in scattering amplitude. There's no physical singularity as you tune your Mandelstams or your center of mass energy. But what you can do is you can separate the times as far as you possibly could imagine, and that's the closest that you get to factorization. So then you can reproduce this object using 3-point data. So what you get is you get G, which is like the 3 points I am flat at 3 points times psi 1 over 2y, which is the 2-point function which is the, what is this? It's the 2-point function of the field phi, the messenger times psi 3 k3 k4 y. There's no y going to zero singularity, as you see from there. So the way that the computation gets rid of it is like this. So you get some funny factorization rule that this, of course, is related to psi 3. So if you know psi 3, the 3-point wave function coefficient in these limits as k1 plus k2 plus y to 0, you get whatever you get here. You can partial fraction it, and the terms that appear in the partial fraction are related to 3-point data. Okay?
They're all same times, right?
Yes. Correct. Thanks. So if you know lower point, so this is factorization. So this is the flat space limit. This is factorization. So this is the locus of the singularities. So you want the wave function to be a smooth object in the physical region that has singularities only at these 3 places in kinematic space, when either the partial energies go to 0, entering a vertex, or when the total energy of a process goes to 0. So there are these 3 singular places in kinematic space, and you know exactly what they should look like in that limit. So you can use that to bootstrap the psi 4 in the more complicated de Sitter case, which we're gonna do after the break. So let's take a few minutes break and then we continue. Are there any questions or?
Because it's a condition, you have to go to the complex formula.
Yes. Yeah, it's not so straightforward to do it in the de Sitter case because, but it can be done because the 3-point function is doesn't have a pole; it has a logarithmic singularity. But okay, but you can still do it. You take some discontinuities, etc.
Great.
maybe this is.
Ah oui. Peut-être je doute parce que si.
Back.
Yes.
So comments about this model. Maybe on Friday we'll use this. So I just want to make a comment. It's away from the thrust of what we're doing. But there's something kind of neat about this model of this IQ theory in flat space. So psi 3 was just 1 over k1 plus k2 plus k3 g. And if you look at the triangle, it's just g over the perimeter. Now psi 4 is written over there. And we are on the S channel. So one thing you can do is you consider, well, this is what we're calling Y. If you consider the dual graph, then it looks like an S channel type of diagram. And if you look at the formula here, what is it? It's the product of all perimeters that appear in this figure. There's the overall perimeter, which is this term. Then there's this perimeter, which is this term. And finally, this is this perimeter. Okay? And the statement is that this works at any number of points. Can you prove it using sort of old-fashioned perturbation theory? But you can never take overlapping triangulations. So it should always work like a nested Russian dolls. Okay? Matryoshka. But there can be multiple ways starting at 5 points. So for example, if you do 5 points, say you're interested. There are 9 integrals to do. You can do it, but there will be when you sum all the 9 integrals up. So you see there the propagator had 3 parts, no? Each time ordering plus the term that enforces the boundary condition. So now there are 2 propagators. So there are 9 integrals to do. When you add them all up, there are 2 terms, essentially. And the 2 terms have to do with let me call them y and y prime. One, two. There are 2 terms because there are 2 separate triangulations you can do. Of course, you start from the big polygon, then you can cut this along this diagonal. You get this big quadrilateral and this little triangle, and then you can cut inside the big quadrilateral, and you get these 2 triangles. So this is one possibility, and possibility number 2. You start with the overall polygon, and now you cut this here first. And this. So now there will be 2 terms. So psi pi prime will be 2 terms. And we can just write down the answer. So notice that the perimeters of the overall thing and the 3 triangles are common, so the only thing that the two terms do is they have these two separate perimeters. So what's up front is 1 over K1 plus K5. Then what are the little triangles? It's K1 plus K2 plus Y, right? K3 plus Y prime. Then K4 plus K5 plus Y prime times what is this perimeter here? It's 1 over K1 plus K2 plus K3 plus Y prime. 1 over, and the other perimeter is K3 plus K4 plus K5 plus Y. And these singularities make sense in the spirit of sending. So of course, this is the total energy singularity, and these are singularities where you send one at a time a vertex to the past. But these two are the guys that just send sub-processes to the past. You send either this sub-process. If I want to send this sub-process to the past, K1 plus K2 plus K3 plus Y prime, that you have to send to 0. And likewise, this one here. Okay. So that one corresponds to this, and this one corresponds to this singularity. Okay. So this is very nice, and it works at any number of points. This is a comment. So there, it turns out you can build some geometric shapes in kinematic space. They're called cosmological polytopes, whose sort of volumes or some forms associated to them compute this for you. But anyway, so this is a neat story, but a bit outside of the scope of what we're discussing. So I just wanted to point this out because we might use some of this structure on Friday. Okay, so let's go back to the sitter. So in the sitter, the only thing that changes, so psi 4 is exactly the same. The rest is maybe the measure has factors of flowers of eta, but the propagator here in the middle, I mean the external legs, you want them to be massless anyway, so they are sort of beefed up exponentials, but they're simple things. But the problem is this one here, which has punctual functions, okay? And okay, so that's the main issue. And you'd like to find another way of computing this. And so psi 4 prime must be compatible with the sitter kinematics while at the same time being singular when K1, 2, 3, 4 go to 0, K1, 2 plus Y go to 0, K3, 4 plus Y go to 0. And we try to find a minimal sort of equation that enforces this, that is compatible with the sitter kinematics and allows you to have the singularities. It'll turn out that there's a new one that is forced on you, but it is beautiful, it has physical meaning. We'll see what it is. Okay. There is a more simple-minded strategy that works just fine for this example, which is this is a complicated object, G, but it solves a simple equation. More humble approach. Use the facts that box plus m squared G equals delta function. So let's say you do box with respect to eta 1. So you take time derivatives with respect to eta 1. This gives well, there's probably some square root of the metric here. This is impressionistic, okay? As usual, there's some square root of the metric that appears in the Green's function. But you try to use this. So the only challenge is to hit psi 4 on the outside with some operator that when you integrate by parts, etc., becomes the box. Okay? And you can do that with some, not a lot of effort, you'll find, but it will be equivalent to this more elegant approach that we're going to follow. And this doesn't scale very well if you go beyond this type of diagram. But it's how at first we were making sure that we were doing the right thing. Okay? So it's equivalent. So there's something nice that there is an operator that depends on external kinematics only. But if you pass inside of the integral, you can engineer the Klein-Gordon operator. And the reason you can engineer the time derivatives, I think, is again related to this nice interplay between distances in the sky and the times in which the fluctuations are generated. So you're leveraging this scaling symmetry of the de Sitter metric to engineer the Klein-Gordon operator. But we'll see that the final expression is almost forced on you by kinematics and dynamics. So let me state what are the constraints of kinematics. Now, de Sitter invariance is equivalent to three-dimensional conformal invariance. That's SO 1,4. And of course, we know, since Dirac, how to make SO 1,4 symmetry manifest. We go to the embedding space, to the null cone, etc. Now, we insist on being momentum space because of this nice connection to scattering amplitudes. And we are going to pay a price here because we're not going to be able to make all the isometries manifest. But one job is to make all the kinematics as simple as possible. The other is to make the dynamics of the simple things we are trying to compute also easy to handle. And I think that the embedding space, even though it makes this manifest, it does not play very well with these simple dynamical processes during inflation. So for example, there are good alternatives around, like Melling space, and on Thursday I'll try to advocate for something a little bit different. But we're gonna, because we're working in momentum space, we're gonna sacrifice something, and that will be special conformal transformations, de Sitter boost symmetry. So let's see how that goes. So psi 4 depends on 12 pieces of data. We're going to use translations. That's easy. We have this psi 4 prime. Now we use rotations to make psi 4 prime depend on, instead of 9, 6 variables, which is just the tetrahedron. Right? Okay, 1, no, sorry, K1, K2, K3, K4. This would be sort of the S channel type of, and this would be sort of the T channel. So let me call S. I was calling Y, but here let me change notation to S and T. These are not Mandel's thumbs because they're momenta. They have different dimension, but by analogy, it's useful to call them S and T. So K2. So now you can make psi 4 depend on the length of this tetrahedron. That's it. Now from dilation symmetry, you can pull out some overall scaling and just look at ratios of momenta, right? Because of the usual. This is the metric in the system, and it has this rescaling symmetry. So this rescales like a power law. Okay. Now I need to say that I'm going to cheat a little bit. We are interested in this diagram. And I'm going to cheat by two simplifying assumptions. One, I'm going to exchange a scalar instead of a spinning part. So I'm going to change I'll mass m, but the spin is 0. Well, that, I mean, otherwise that propagator would have to have some spinning indices, etc., and the structure of the 3-point vertex would be different. That's not so bad. The other thing I'm going to do, I'm going to make the mass of these external particles be 2h squared. Okay, so the wave function will have some eta star dependence because the correlator will redshift away. But this is just because the mode functions are then exponentials. And then for this case, the mode function is just e to the I k eta times eta. So they're simpler technically. If you look at the scaling behavior for m squared equals 2h squared, delta equals to 1 or 2, and m squared equals 0, delta equals to 0 or 3. And the main reason why, okay, at first it was just a crutch to get to the physical case, but then there is a beautiful story. I think it was more or less, well, at least a big chunk of it was already present in that old book of Dobre and Mark and Petko. But then the CFT experts like Simons Duff and Karateev Kravchuk, they revived it, and we discovered it like plumbers, you know, by just playing with it until I met David Simons Duff. I said, oh, it's just this, to draw some pictures, and then we adapted the formalism to cosmology. There's something called wave shifting. Operators. So it's a kinematic tool that works as follows. If I have CFT correlation function, this is a bit of a side remark just to justify that if I understand this process, I understand everything. If I have CFT primary, O delta 1, J1 at point P1, O delta 2, J2, point P2. If I know the correlation function with these two operator insertions, doesn't matter what else is present. Then there's something called weight shifting operator. It's a bilinear. There are various bilinear, there are many choices. So there's a manual weight shifting operators that produce something that's compatible with conformal kinematics. But different weights. Delta 1 tilde, J1 tilde. So the weights usually differ by 1 unit. So for example, there's an operator that shifts delta 1 by 1 unit and reduces J2 by 1 unit. So it's like mix and match. You have to play these games to land on the physical case. So here you see we have delta equals 1 or 2 and we want to land on 0, 3. So there is a fighting chance that if you start from 2 here, you can land on 3. And it turns out that this works. It works rather beautifully. I mean, in fact, you can even, with some extra games, you can even change the mass and the spin of the exchange particle by these sorts of weight shifting things. You can even spin up the external legs. You can talk about graviton correlators by this type of game, although there's some subtlety there. Anyway, so this is a rather powerful tool, which just given to you by the Sitter kinematics. So if you understand this process dynamically, you understand all sorts of other processes that are more interesting from the point of view of physics and phenomenology by just massaging and taking a bunch of derivatives of this simplified diagram. Okay, so we're going to focus our attention on this case, scalars being exchanged, external conformally coupled scalars. It redshifts away, it's unobservable. But if you take these objects as a function of the momenta, you strip out the redshift and you hit it with enough bells and whistles, then you get the object of our interest. So that's kind of neat, which is not obvious that you could have worked out, but it does work out like that. Let's go back. Now we're trying to describe psi 4, the wave function of 4 scalars, but now they're conformally coupled, and that's important when we talk about dilations because it tells me about the scaling weights of this object, which turns out is going to be a -1. Okay, so I'm just stating. It's boring to work it out, so but you can work it out. And let me write it with S over K1, S over K3. No, let me not do that. K1 over S. Okay, so far all we use is isometries and the mass of the external particle. Now, when I exchange scalar particle, just like in flat space amplitude, then the scattering amplitude only depends on the Mandelstam S. The dependence on the Mandelstam T will only appear in the permutation or if the particle is spinning. Right, to get some Legendre polynomial in the scattering angle that is T dependent. So if we exchange a scalar particle, it turns out that there is no dependence on this variable because J equals 0. So this is a dynamical assumption.
Sorry, one thing, the error with the D on top, is it is just an equality for this case, or is it?
Yeah, it's, when you impose dilations, then this function of 6 variables, you can write it as a 1 over S times a function of yes. And now, well, I wouldn't call equal in this case. Now, under the dynamical assumption that you're exchanging a scalar, then this does not depend on T, okay? But now you're reduced to a function of 4 variables, and you haven't imposed the Sitter boosts yet. You have, so now the 3 spectral conformal transformations, and there are some complicated second order differential equations that this function of 4 variables must satisfy. And if you stare at the formula, the integral up there, one thing that you find, for example, you see from here, you see when I multiply these two propagators, it only depends on K1 plus K2. That was not the case if I had two massless particles because there was a K1 eta and a K2. But for conformally coupled, because there's only exponentials, the product KK there depends on K1 plus K2. So if I write now psi 4 prime 1 over S, yeah, maybe to Carlos' question, I would call this psi tilde because psi 4 is really this whole thing, right? Now this is not really the wave function coefficient, just some rescaled wave function coefficient. But now I can write this. If I claim that it depends on only these two variables, I actually diagonalize 2 out of the 3 SCTs, and there's one left. And then there's no way around the fact that you need to solve a differential equation. Okay. Last one, so this gets rid of 2. Last SCT. Let me call this thing now. Unfortunately, because it's wired in my brain, I can't change this. So we call this 1 over U and 1 over V. Okay. So let's call U S over K1 plus K2. V. This U and V notation was because we wanted to sell that these like conformal cross ratios. First of all, these are not cross ratios because it doesn't trivialize conformal symmetry. Second, they're functions of two variables, but we already put a lot of dynamics in. We're just exchanging scalars, etc. So they're more like the best we can cook that looks like conformal cross ratios, but they are not cross ratios. Now, any function that is compatible with the Sitter kinematics in which you exchange whatever you want, as long as you exchange spin 0, will satisfy the following differential equation. In other words, if you take your favorite 2-point function, stick it in there, do Chow-Lemon decomposition, and focus on the spin 0 sector, you're going to find that this final object, let me call it F. Okay? Let me call this thing F of U and V. It's just this psi tilde prime 4 of this, but now of U and V. Okay? Must solve delta U F equals delta V F, with the delta U is just a hypergeometric operator. Okay, so there are lots of solutions of this. You can even try to find the basis, eigenbasis for most general solution using hypergeometric functions. It doesn't really help a whole lot, but anyway. Because the simple processes, they are not so bad in these variables. Let's check. Let's validate. So that's it, kinematics. So any function that you can write in this form is compatible with the Sitter kinematics. Let's check with the simplest example. So conformally coupled scalars with lambda phi to the 4 self-interaction. I mean, this is really trivial because it's conformally coupled and the interaction is conformal invariant. So it's literally the flat space scattering amplitude but you integrate over half space, because in the sitter, time runs from minus infinity to 0, right? So psi 4 is going to be integral minus infinity to 0 lambda e to the I k1 plus k2 plus k4 eta. I mean, there eta to the fourth here, but there's 1 over eta to the fourth from the measure, right? And I'm stripping out eta star and h, etc. I'm just trying to focus on the kinematics. So this is going to be just like the flat space tensor. So there is no S here, but okay, you can engineer it. Let's just put it in the form that we were advocating. So the I lambda is not important over S. And this is 1 over U plus 1 over V is I lambda over S UV. Okay, now you can check that this function satisfies this PD. Okay? Yeah.
Before I thought you said that to relate these to slow roll inflation, the thing that the leg that you want to go to the soft doesn't have mass exactly 0.
Yes.
But here you will relate everything to f squared 0.
Now you can do, but it takes a bit more work. But you can essentially take the same objects and do the slow roll trick. I'm just not describing how to do it, but there's a small variant of the weight shifting where you shift from delta very close to 2 to delta very close to 3, take the soft limit, Taylor expand, and everything still works out. So you can still take these objects and do something with it, and you get the slow roll 3-point function. But this requires a bit more work, so I'm not telling you how to do it. But if you look at, I have a paper called weight shifting operators in the cosmological bootstrap, and we describe this procedure there. Okay, so going back here, so this satisfies delta U equals delta V. Moreover, it has only the singularity U plus V going to 0, which is consistent with self-interaction. Just you're sending the vertex to the past. And that suggests a strategy to create all sorts of self-interactions. In fact, when you exchange scalars in the S channel, you can generate all of them by the following rather trivial trick. Without writing, no Lagrangians will be harmed in this process. So consider delta U applied many times to UV over U plus V. What you're going to produce? You're going to produce, this is a second order operator. You're going to produce every time you hit it, let's do one time, okay? So you're going to get 1 over U plus V cubed times some interesting numerator. And we can work out in like 5 minutes. So maybe it's 1 plus UV squared. It doesn't matter. So you see now, as related to Marcello's question, you see that the total energy singularity is of different order. It's total energy cubed, okay? And that's because of scaling variance. So if you want to generate higher powers of Mandelstam coming from irrelevant interactions, you have some tension, naive tension with scaling variance of the correlator. And the way that the correlator does that for you is it puts a higher power of total energy in the denominator. So when you now send U plus V to 0, and you send K1, 2, 3, 4 to 0, and you restore the S, etc. So if you take this, put it in here, 1 over S, send K1, 2, 3, 4 to 0, you'll find 1 over K1, 2, 3, 4 cubed times, well, what we expect, which is the Mandelstam. S flat. Different mass dimension. It's just the Mandelstam. Because I'm only looking at the S channel, there's an S. Usually it doesn't appear in the amplitude when you sum over permutations. But you see, and then this works at any number of points. So if you take delta U to the n, you're essentially generating all powers of Mandelstam in the flat space limits. But it's a bit peculiar. So we say that we're probing very high energy physics, but somehow the very irrelevant operators, it's not that they are, the experiment is run fixed energy, Hubble, right? So the way that the irrelevant operators become important is only when you go away from the physical region, when you go to this total energy. So going to zero limits. Say that you had various operators of different mass dimension contributing to this 4-point function. So they all look rather innocent ratios of momenta. The way that the irrelevant operators will be suppressed is just by ratios of Hubble to the UV cutoff. And it's not that you, as you crank up energy or as you move momenta around, the irrelevant operators take over or get suppressed. The only way that you see the usual way things work in flat space is by going away from the physical region and sending total energy to zero. Then you'll be sensitive to the most irrelevant interaction. Okay. By the way, if you do exchange, the behavior is softer. So you need to soften a simple pole in energy. And what happens is that when you have exchanges, you start obtaining logarithmic singularities. So this cuts both ways. The more irrelevant the operator, the higher the power. So if you have exchange, which softens the amplitude, then you have logarithmic singularities. And the conjecture is that if there were string theory in de Sitter space, there would be no singularity, which is a bit of a funny thing. Because you'd have to produce a correlator which has so many states somehow that it softens this total energy singularity. So even when you send total energy to zero, the integral minus infinity doesn't give you anything, any contribution. So the argument I was giving you before for the existence of the singularity needs to fail. Anyway, so this is how you build all contact interactions by just hitting delta U many times. So you're just using de Sitter kinematics. You're producing other objects compatible with de Sitter symmetry that are only singular when U plus V go to zero, which is total energy going to zero. Okay. So how do you how are you going to do exchange? Well, we can use flat space analogy to justify it. So delta U is sort of analogous to multiplication by S flat. So if I have an exchange of a massive particle, then the scattering amplitude is just G squared over S flat minus M squared. And of course, it solves the rather trivial algebraic equation S flat minus M squared times this scattering amplitude equals G squared, which you can consider to be contact interaction, because it has no dependence on Mandelstams. So this engineers the exchange propagator, Klein-Gordon operator, collapses this propagator, and you get an exchange diagram. So we're going to do the same thing here. So there's going to be delta U plus something. This something is related to the mass of the exchange particle. If you look into it in detail, it turns out to be this. This is the analog of lambda phi to the 4 contacts. Okay? So that's it. So this is the differential equation. Of course, these are dimensionless, so you can't put a mass scale here. You put the mass of the exchange particle in Hubble units. And if you do the things, all the nitty gritty, you could imagine from purely bootstrap perspective just to call this, I don't know, pole mass or whatever. And it turns out that, you see, when the exchange particle has conformally coupled mass, then this is 0. Okay? But for generic mass, this is, so for example, if you exchange a massless particle, it looks a little bit tachyonic, this term, but everything's okay, infinitary, etc. In order to be compatible with the kinematic constraint delta U equals delta V, then you just want to solve also the ODE. Oops. Should also give the same right hand side. Okay? So that's it. So these are, so this is the operator that if you go back to the time integrals and you shove it inside of the time integral, you can integrate by parts and turn this into the Klein-Gordon operator. This depends on U. So U, this is K1, K2, and S. So delta U is only acting on this vertex in some sense, because it depends on K1, K2, and S. And somehow you shake and bake this vertex so that you manage to collapse this propagator. And delta V is doing the same thing from the other side, because you weren't able to boost some center of mass frame, so you have to move either the left vertex around or the right vertex around. Okay. So exchange becomes equivalent to solving two ODEs. So then you can beat with 18th century mathematics to that. And that's the thing we thought was a new function, but it turns out to be this competitive function. Okay.
Is it possible to understand the original visualization from conformal symmetry? Because you said at the very beginning, well, I'm pretty sure it's followed for conformal symmetry because, as you said, if applying to the amplitude, it's conformal generation.
Right. I think if you act with the conformal Casimir here, then you engineer the left-hand side. But then you need to argue that what this conformal Casimir does is it collapses this propagator, and then would give you. Then you can show that the conformal Casimir of this guy plus this guy plus this guy squared gives this operator.
What's counterintuitive, maybe it's my misunderstanding, that you're acting on the conformal generators in momentum representation of external lag, but when it hits intermediate propagator, it hits intermediate propagator in configuration space.
Yes.
Yes. So at some moment you can convert momentum generators into coordinate representation.
Only for time, yeah, because yes, for time, yeah, but that's true. And this works very nice for the single exchange, but then just an observation maybe to justify what we're going to do on Friday. One thing that confused us is if you have this diagram, how are you able to act only on this momentum here and manage to collapse these propagators? And if you do, which one do you collapse? And that was a big puzzle, and we tried, we struggled for many months. And ultimately, we massaged this into some integral that looks like some flat space loop integral, and we use QCD machinery to solve this problem. It turns out that there is a differential equation, but it's of much higher order than you would naively expect. Anyways, this is.
But normally, when you have conformal symmetry in the game, which is your case, you have the star triangular relation. Which
Maybe that would help. I think some people. I remember Costa Scandel is telling me that this was useful, but I don't know if he was able to show that this is related to these star triangle relations. Yeah. An interesting question. Okay.
here the dependence is the like mass of the axis appears.
What dependency again? Yes. Well, I mean, psi 4 goes like 1 over eta star to the fourth, I think. Because the correlator, no, I actually don't remember, but you can work backwards, but phi, the phi to the fourth would go like eta star to the fourth. So it really goes to 0. And then we're talking about the kinematic function that appears up front. Then you can reconstruct from the wave function coefficient. So this is the spirit of ADS-CFT. So you have the leading growing modes of behavior, and you strip out the fact that it's decaying, and look at the coefficient up front. Well, or in the limit, maybe more physical, in the limit when all the momenta that you're correlating are set to k eta star is much smaller than 1, because it's a dimensional quantity, right? So how are we doing with time? I'm done. Yeah, okay, I need to tell you about boundary conditions. Then we go for lunch. We have a boundary condition of taking the bus to lunch, right? So let me tell you about it. So, no,
You have 10 minutes, I don't know.
I have 10 minutes. Okay. So very good. So let me tell you, let's look at the differential equation. There's also all sorts of cool stuff that happen with the differential equation. Has some sort of resurgence, and maybe you can mention it a bit next time. But let's look at the singularities. So delta U is of this form. So it's singular as U goes to 0, U goes to plus or minus 1. Okay? And the source has the singularity as U goes to minus V. This is our old friend flat space limit. And from here you can see that if you solve near U going to minus V, just you integrate twice, you see that F, as promised, will go like, and maybe you can even pin the coefficient. This is just sort of the 1 over S, and you see it's softer, the high energy behavior, because it's exchange. So this is not going to help us in solving the equation, but it's just the behavior for the flat space limits. Now it's a second order equation. We need 2 places to put boundary conditions. So when U goes to plus 1, it's S going to K1 plus K2. And this is just a collinear limit. It's just K1, K2, K3, K4. And here nothing should happen. There's nothing special going on. So smoothness of the correlator in the entire physical region should tell that there's no singularity, even though the differential operator likes to put singularities here. And people associate this with alpha vacuum. It's a question about alpha vacuum. So if you have different vacuum states for the sitter, maybe you want to put some coefficient of the singularity there. What will happen is that the function will have some behavior, some logarithmic behavior, U minus 1. And you want the coefficient to be a big 0, okay? So that's one boundary condition. That's boundary condition 1. You need a second one, which is U going to minus 1. Sorry, the Blackboard management is going to shambles. So U going to minus 1. This is S plus K1 plus K2 to 0, which is factorization. We just discussed It's technically more complicated, but the point is that it's the behavior of the solution should be determined by 3-point data. Should be this difference between the 3-point function at separate locations, etc. You need to study the 3-point function that we did not study, which is 2 conformally coupled scalars and 1 massive particle. This has mass m, and this has m squared equals to h squared. It's not complicated. You can do it. You can find the exact solution. And psi 3 is determined by a simple differential equation there. It turns out that psi 3 properly interpreted is related to homogeneous solutions of these equations. So even though u is s over k1 plus k2, if you replace s with k3 in this diagram, the equation is roughly the same. Okay, so the 3-point function is related to homogeneous solution of this equation. So you can use this as a boundary condition too. So it should factorize properly in terms of 3-point data that you understand, and it should have no singularity in these limits. And you're done. But then there is a third singular point. But the singular point is physical. When u goes to 0, is s going to 0. But when s goes to 0, there's a singularity because of particle production. The particle production is forced. You have no choice. It's spontaneous particle production. Schwinger or Hawking or Parker, maybe better in cosmology. Parker, pair production that is forced on you. Okay, this didn't appear in flat space, but and this is actually non-perturbative effect in the mass. Okay, it's there wired in the equation. I'll show you technically, maybe on Friday, how it appears, because it's kind of neat. It's connected to this thing called resurgence. But so anyway, so you can solve, you can beat this equation to death, you can build beautiful plots. The plots are very similar structure to what I showed you last Friday. They have these oscillations and smooth decay near the equilateral limits. And it all follows from solving these differential equations rather than doing explicit integration. Okay? So Friday, what I will do is maybe I'll spend a few more minutes explaining how to actually just highlight some cool things about solving this differential equation. And then I'm going to go back to this funny toy model in flat space, spice it up a bit, and try to build a general theory of differential equations there, which uses a lot of tools of QCD. We're going to have a little surprise there. Okay. So I'll stop here.
Questions? Do we have a question? When you take the flat space limit where the total energy goes to 0, you can extract the flat space amplitude as a residue. Does it work for both masses and masses?
But because you take the high energy limit of the flat space amplitude, you raise the mass. So you always only see 1 over s. Now there are proposals in the literature by the people at Imperial College that they claim that there is a certain double scaling limits that keeps the mass around, but I haven't studied it in detail. But these naive limits will just, it's the high energy limit of the flat space scattering amplitude, so it raises the mass.
Other question? Okay, so if not, thanks.
See you Friday.
See you.